Welcome to Calculus 3, video lecture number 16 on directional derivatives and the gradient vector. So if you'll recall, partial derivatives with respect to x or y provide the rate of change in the direction of either the x-axis or the y-axis. So for example, say we have a flat plate here, and the temperature of that flat plate is given by a function of x and y, the location where you are on the plate. Okay, then if we looked at the partial derivative with respect to x, that would give us the rate of change in temperature in the horizontal direction. And the partial with respect to y gives us the rate of change of the temperature in the vertical direction. But what if I wanted to move in some other direction and know what the rate of change in the temperature was going to be? Why do we have to restrict ourselves to only moving in the horizontal or vertical direction? Well, in that case, we're going to have to figure out how to find a directional derivative. So we know that we can describe directions using unit vectors. And so suppose I want to know what the derivative or the rate of change of the temperature is on this plate in the direction of some arbitrary unit vector with components a, b. Okay, so the process is as follows. I'm going to draw a line that contains that vector u. So I'm going to extend it. This is my line, let's call it L. And I'm going to locate another point on the line. So here is P. That's where I'm interested in figuring out the rate of change of the temperature. And I'm going to pick another point Q on the line. Well, I know this line L has the same direction as our unit vector U. And this vector PQ, notice here's PQ, that's a vector. It's a scalar multiple of the unit vector U, right? They're parallel. They have the same direction, just PQ may be a different length. So I'll say H times U is how I can express PQ. H is a scalar. And if I were to look at the magnitude of PQ, that would equal the magnitude of H, the scalar, times U, which would just equal the absolute value of H because we know the magnitude of U is 1. All right, so if I say point P has coordinates x naught and y naught, how could I figure out the coordinates now of a point Q? Well, how would you get to Q? Well, remember, I'm saying that PQ is equal to H times U. So Q's x coordinate would be x naught plus H times A. Remember, the components of U were A and B. And then the y component would be y naught plus H times B. Right? Because this distance here and this distance here would get us to Q. So now say I'm interested in the average rate of change as we move from P to Q. Average rate of change of the temperature, right? Well, I would have delta T over H, and that would give me, well, delta T would be T of Q minus T of P divided by H. And then T of Q, well, I'm going to use the fact that we said T was a function of x and y. So I could also express that as f of, remember the coordinates for Q, we found them right here. Here's Q's coordinates. So that would be f of x naught plus HA, y naught plus HB, minus, now T of P, remember P's coordinates are just x naught and y naught, so this would be f of x naught, y naught, divided by H. Okay, well this is the average rate of change. So remember, to get the instantaneous rate of change, which would be our derivative, I need to do one more thing. So to get the instantaneous rate of change at P in the direction of U, our unit vector, we would need to take the limit as h approaches 0 of this quantity. And now we have the definition for our directional derivative. So the directional derivative of f at x naught, y naught in the direction of a unit vector u with components a, b is given as follows. So here's the notation. You write capital D, subscript is u, the unit vector. So that means your directional derivative, u tells you the direction of your function f at x naught, y naught, that's the point, is going to equal the limit as h approaches 0. And in the numerator, we have that same difference from up above, f of x naught plus ha, y naught plus hb, minus f of x naught, y naught over h. All right? Now, in practice, you're not going to use this limit definition to find the directional derivative, much like most of the time we don't use the limit definition to find derivatives anyhow. So here is a theorem that allows us to compute it in a much more convenient form. And it tells us if our function f is differentiable, and it has to be differentiable for x and y, then f has a directional derivative in the direction of any unit vector with components a and b, and it can be found as follows. So your directional derivative, and say we're also finding it at the point x naught, y naught. So the directional derivative of f at x naught, y naught would be equal to the partial derivative with respect to x evaluated at x naught, y naught times a plus the directional derivative, or the partial derivative with respect to y at x naught, y naught times b. And most textbooks have a really nice straightforward proof of this theorem, so I recommend reading through it. And interestingly, notice this is how our understanding of the partial derivative with respect to x and y comes into a better light here. Say I wanted a unit vector in the direction of the x-axis. Well, easiest choice would be to let u equal 1, 0, right? So if you want your directional derivative in the direction of the x-axis, you would have partial with respect to x times, well, a is 1, plus, this needs to go away for now, plus partial with respect to y times 0, and you just get partial with respect to x, which is why f of x, partial with respect to x, is the directional derivative in the direction of the x-axis. And then I'm sure it's no surprise, if you want the directional derivative in the direction of the y-axis, u would be 0, 1. You apply the same definition. You have partial with respect to x times 0 plus partial with respect to y times 1, and you get your partial with respect to y. So basically the idea of the directional derivative is we don't want to restrict ourselves to only finding rates of change in the direction of the x-axis or the y-axis. We want to be able to pick any direction. And so all we need to do is define a unit vector. So here we go. We're going to look at some examples. Let's find the directional derivative of f of xy equals x over y at 6, negative 2. So this is my point, x naught, y naught, in the direction of v. And v has components negative 1, 3. Well, first thing we need to address is the fact that I need a unit vector. So the magnitude of v is going to be rad 10. So in order to make it a unit vector, I just need to divide by that. So 1 divided by rad 10 times negative 1, 3. And so we get negative 1 over rad 10, 3 over rad 10. That's what we're going to use for u. All right, now I need my partial derivatives. So partial derivative with respect to x, remember holding y constant, that would just give me 1 over y. So that means that my partial derivative with respect to x evaluated at 6, negative 2 would just be negative 1/2. And then partial derivative with respect to y, Well, remember that's x times y to the negative first power, right? If I'm treating y as a variable, so now that's going to be negative x over y squared. So my partial with respect to y evaluated at 6, negative 2. That's going to be negative 6 over positive 4, so negative 3/2. All right, so these two values I'm going to hold on to right now, and then I'm going to put it all together, find my value of the directional derivative of f at the point 6, negative 2. So I take negative 1/2, partial with respect to x at the point, and then I'm going to multiply now by a, remember, the x component of our unit vector, which is going to be negative 1 over rad 10, plus, and then I take negative 3/2, partial with respect to y at the point, and then I multiply that by b, which is 3 over rad 10, the y component of our unit vector. And then let's see here, so I'm going to have 1 over 2 rad 10 minus 9 over 2 rad 10. So that's negative 8 over 2 rad 10, which is negative 4 over rad 10. And that's our final answer for this problem. Not too terrible, right? Okay, so let's look at another example here. Find the directions in which the directional derivative of f of xy equals x squared plus sine xy at 1, 0 has the value of 1. So in this case, they're setting it up a little differently than before. We have to find the directions, meaning we need to figure out what u is. And they gave me the value of the directional derivative already. So basically, we know that the directional derivative of f at the point 1, 0 in the direction of u is equal to 1. What I need to do is figure out what is u. So we'll say u has components a and b. That's what we're after. All right, well, I'm going to start by finding the partial derivatives and then solving for my unknowns from there. So partial derivative with respect to x, derivative of x squared is going to be 2x. And then when I take the derivative of sine xy, remember we have to use the chain rule, so I'm going to multiply by y. So I have plus y cosine xy. And then partial derivative with respect to y is going to be, derivative of x squared will give me 0, and then I have x cosine xy. Good. Now both of these I need to evaluate at the point 1, 0. So partial with respect to x at 1, 0 is going to be 2 times 1 plus 0, so that's just 2. And then partial with respect to y at 1, 0, that's just going to be 1 times 1, so 1. All right, well, I know that my partial with respect to x at 1, 0 times a plus the partial with respect to y at 1, 0 times b is equal to, and they told me the value of the directional derivative there is 1, so I can set that equal to 1, which means now I can replace this first quantity with 2, right? Partial with respect to x at 1, 0 is 2 times a plus partial with respect to y at 1, 0 is 1 times b equals 1. Okay, so that's good. However, I have 2 unknowns and only 1 equation at the moment, which is problematic. How can I solve for a and b? But I'm not using one other piece of information, and that's the fact that u is a unit vector. So what does that mean? That means that its magnitude is 1. Therefore, a squared plus b squared has to equal 1, right? Since u is a unit vector. So now I could put everything together and just solve by substitution. So I have this cute little system of equations here. All right, let's separate our work. And say I solve for b, so I know b is going to equal 1 minus 2a. And I substitute that into the second equation. So here's equation 1, here's equation 2. I'll have a squared plus 1 minus 2a squared equals 1, which gives me a squared plus 1 minus 4a plus 4a squared equals 1. So the 1's cancel out. Then I have 5a squared minus 4a is equal to 0. Factor out the a, and I have 5a minus 4 is 0. So what does this mean? Well, a is either equal to 0 or a is equal to 4/5. So I have two options for my unit vectors. Unit vector number 1, if a is 0, b has to be 1, right? Its magnitude is 1. Unit vector number 2, if a is 4/5, then I could solve for b. Come back here, that way you won't have any ambiguity as to the sign of b, right? So if a is 4/5, that's going to be 8/5. So b is 1 minus 8/5, which is going to be negative 3/5. And then you can confirm the magnitude should be 1, which it clearly is. Okay, so there's our solution right there. Pretty fun, huh? All right, now it can also be useful to represent the desired direction by using a unit vector expressed in terms of an angle theta. So find the directional derivative of the following function, f of xy, at the point P with coordinates 1, -1, in the direction of the unit vector whose direction is given by the angle pi/3. So basically you just have to think of what are the values on the unit circle at pi/3 to figure out the components of the unit vector u. So cosine of pi/3 is 1/2. And sine of pi/3 is rad3/2. And so those are the components of u. And now they just want the value of the directional derivative. So let's go ahead and take our partial derivatives first. So partial with respect to x is going to be 2x plus 6y. Partial with respect to y is going to be 6x minus 6y. And then now I want to evaluate each of these partials at the point P. So at 1, -1, the partial with respect to x is going to be 2 minus 6, so -4. And then partial with respect to y at 1, -1 is going to be 6 minus -6, so 6 plus 6, which is 12. All right, now putting it all together, I have directional derivative of f in the direction of u at 1, -1 is going to equal, so you take -4, times a, here's a, 1/2, plus 12 times rad3/2. And this is going to give me -2 plus 6 rad3 for our final answer. Ooh. Beautiful. All right. Moving on. Have you felt like you were doing a familiar process here when you were computing this directional derivative? Did you notice you were doing a dot product the whole time? And in fact, we have another very useful way to represent the directional derivative using a dot product. So think about it. You take the partial with respect to x, you multiply by a, and then you add that to the partial with respect to y times b. So one of the vectors would have to be a vector of partial derivatives, right? Partial with respect to x, partial with respect to y. And then you take the dot product of that vector with AB, where u has components a and b. Okay, so we're going to try using this notation instead. It's just a little cleaner. So find the directional derivative of the following function of x, y, and z. So in this case, I'll have to take 3 partial derivatives, so I'll have vectors in 3 space at 1, 6, 2 in the direction of the following vector. So first things first, we need a unit vector, don't we, people? So let's see, what's the magnitude here? So 9 plus 16 plus 144, that's right, it's 169. So I'm going to divide V by 13. So now I have U, which is going to be 1/13 times 3, 4, 12. All right, now let's find our vector of partial derivatives. So I need partial with respect to x, y, and z in this case. So partial derivative with respect to x is going to be negative 2xy. Partial with respect to y is going to be negative x squared, and then partial with respect to z is 3z squared. Now, if I evaluate this at the point P, so what you could do is you could just indicate that you're going to evaluate this at negative, or where's the point? 162, right? Here's the point P. So I'm going to evaluate it at 162, and I get negative 12, negative 1, and then 3 times 2 squared, 3 times 4, 12. All right, so there's my vector. Let's save that. And then now I'm ready to find my directional derivative. And I didn't distribute that 13 on purpose because watch, it's going to be so nice right now. So directional derivative of f at 162 in the direction of u is given by dot product of negative 12, negative 1, 12, with 1 over 13 times 3, 4, 12. Well, that 1 over 13, I can just pull it outside of the dot product, right? And then negative 12 times 3, so taking the product of those first components, that's going to be negative 36, and then same thing with the second components, negative 4, and then I have plus 144. So that's negative 40 plus 144, so that's 104 divided by 13, which is 8. Da, 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 da. There we go. Now, interestingly, the vector of partial derivatives that we saw up above that was used in this dot product has a number of applications. And it's such a popular vector, it even gets its own name. So if f is a function of two variables, x and y, then we say that the gradient of f is the vector function, and it's denoted as follows with that upside down triangle, defined by, so we say the gradient of f equals the vector of the partial of f with respect to x, and then the partial of f with respect to y. And you can also extend this for more variables. Okay. Now we're going to study this gradient in more depth for the remainder of this lesson. So what we want to do is consider how the value of the directional derivative changes as we change u. So now that we know the directional derivative can be written as the gradient of f dotted with u, we know that we can rewrite this dot product as the magnitude of the gradient of f times the magnitude of u times cosine of theta, right? When theta is the angle between the gradient of f and u. Well, I know that the magnitude of u is going to be 1 because u is a unit vector, right? So I can rewrite this as just the magnitude of the gradient of f times cosine theta. Theta is the angle between u and the gradient. Okay, so I want to study how is this value of the directional derivative changing as u changes, as the direction of u changes. So if the direction of u is changing, all that would be changing to represent that would be theta, right? The angle between u and the gradient. Well, let's think, what do we know about cosine of theta? Well, it's bounded. Cosine of theta is equal to 1 when theta is equal to 0. So that means this quantity here is maxed out when theta equals 0. So we achieve the max value of the directional derivative. Okay, other extreme cases. Cosine of theta is negative 1 when theta equals pi. So in that case, we achieve the minimum value of the directional derivative when your unit vector, u, is in the opposite direction of the gradient. So when theta is 0, that means they're parallel and in the same direction, u and the gradient. And when theta is pi, they're still parallel, but they're in opposite directions, u and the gradient. Another way that you would say you have the min value of the directional derivative is it could be referred to, and this is confusing at times, as the max rate of decrease. Okay, and then last scenario that's interesting is cosine of theta equaling 0, and that happens when theta is pi over 2. And in that case, the directional derivative is constant, and that means the function values aren't changing, or they don't change. Okay, very good. Now, let's look at a nice, exciting follow-up theorem. What could be better? So suppose f is a differentiable function of 2 or 3 variables, then the max value of the directional derivative is given by the magnitude of the gradient of f of x, and it occurs when u has the same direction as the gradient vector given below. Okay, so we informally came to this conclusion because we knew from previous studies that cosine theta maxes out at 1 when theta is equal to 0. But here we have a theorem that guarantees this. And so if you're ever asked to find the maximum value of the directional derivative, all you have to do is find the magnitude of the gradient. Isn't that nice? So burn this in your brain. Max value of directional derivative, all you need to do is find magnitude of the gradient. Don't go back to other calc ways of finding maxima and minima and taking extra derivatives. Not necessary when you're working with the directional derivative. Okay, so let's apply it now. The temperature at some point in space, x, y, z, is given by the following function. So you have temperature is determined by your location in 3-dimensional space. And T is measured in degrees Celsius, x, y, and z in meters. So find the rate of change of the temperature at P in the direction toward the point Q. Let's call it Q. Point towards 3, negative 3, 3. Okay, so first thing, let's make a vector in that direction from P to Q. So the components would be 3 minus 2, which is 1. Next component's going to be negative 2 and 1. All right, well, first thing, what do I need to do with this guy? That's right, we got to make it a unit vector. So its magnitude is 6. So my unit vector u is going to be 1 over rad 6 times 1, negative 2, 1. Very nice. Okay, next I need the gradient. So gradient of t, remember that's the vector of your partial derivatives. I'm going to take partial with respect to x, partial with respect to y, partial with respect to z. So partial derivative with respect to x is just going to be 2y. Partial with respect to y is going to be 2x minus z. And partial with respect to z is going to be negative y. And then now I need to evaluate the gradient at the point P, because they wanted the rate of change at P. So that's the point that I'm evaluating it at. So at 2, negative 1, 2. So that will give me components negative 2. 2 times 2 minus 2 is 2 again. But we got to write a nice 2, don't we? That's much better. And then negative y, that's going to be positive 1. All right, so now we're ready to put it all together. I'm going to take the dot product now of this vector, of my gradient vector at P with u. And that is the directional derivative of t at P in the direction of u. It's a mouthful, isn't it? So I'll take negative 2, 2, 1, dot that with 1 over rad 6 times 1, negative 2, 1. Aren't you glad you didn't distribute the rad 6 right now? Okay, keep it in the denominator. Keep it in the denominator. And then we'll just do the dot product in the numerator. So I'm going to have negative 2 minus 4 plus 1. So what does that give me? Negative 5 over rad 6. And we need to include units. So notice this is the rate of change of temperature. And they told me temperature here is measured in degrees Celsius. So this is degrees Celsius per meter. Very good. Okay, moving on. In which direction does the temperature increase the fastest at P? Well, as we looked at before, the directional derivative achieves its max value when u, your unit vector, is parallel in the exact same direction to the gradient vector. So it increases the fastest in the direction of the gradient of t at P, which was 2, negative 1, 2, which has components negative 2, 2, 1. Second part of the problem, what is this rate of increase? Well, thank goodness we have that theorem from up above that tells me that the max rate of increase, I don't have to write max, just the rate of increase is the magnitude of this vector, magnitude of the gradient, at 2, negative 1, 2. So if I take the magnitude, I'm going to have square root of 4 plus 1. So that's going to be 3 degrees Celsius per meter. Very nice. Now, part C asks an interesting follow-up. At the point P, is there a direction in which the rate of change in temperature is negative 5 degrees Celsius per meter? If so, where? And if not, why not? Well, remember, since I know the max rate of increase is 3, that also means that the max rate of decrease is going to be negative 3, and that occurs when u is opposite, in the opposite direction of the gradient. So that means, no, negative 5 degrees Celsius per meter is not possible. Let's write this all out. We know that the most rapid decrease, or the minimum value of our directional derivative, is in the direction opposite to the gradient. So opposite of the gradient of t. And its rate would be the opposite of the magnitude of the gradient. In this case, that's negative 3 degrees Celsius per meter. So no. Let's say it with emphasis. There we go. Negative 5 degrees Celsius per meter is not possible. All right, make sure you have those concepts under control, because the terminology can sometimes be confusing, even though the idea really isn't. All right, moving on to another interesting example. Suppose you are climbing a hill whose shape is given by the equation z, which equals 1000 minus 0.01x squared minus 0.02y squared, where x, y, and z are measured in meters, and the positive x-axis points due east, while the positive y-axis points due north. That's pretty standard, people. So suppose you are at the point with coordinates 50, 80, 847. So this is giving you x, y, and then this is z, your elevation. So basically you have a hill, and the height or the slope of the hill, the shape of it, is given by that equation there. Z is giving you the heights of the hill. All right, so the first part asks, if you walk due south, will you start to ascend or descend, and at what rate? So I'm going to first call this z a function f of x and y to maybe make the notation a little bit easier. And basically, if I'm going to figure out if I'm ascending or descending, I want to know what is the rate of change of z, right, if I walk due south. So in the direction of, I have to figure out how to write a unit vector that represents going due south. And I want to know if I'm ascending, then that rate of change of z is going to be positive, right? I'm going uphill. And then if I'm descending, the rate of change of z, that directional derivative, should have a negative value. All right, so let's draw out our coordinate plane here. And y-axis points due north, x-axis points due east. And we're at the point 50, 80. And then our elevation is 847. Okay, so what unit vector could you use to represent walking due south? What would its components be? That's right, 0, -1. That would take you due south. Then I want to know what the gradient of f is. Well, the gradient of f, partial with respect to x, is going to be -0.02x. Partial with respect to y is -0.04y. And now I'm going to evaluate the gradient at the point, well, what was the point? 50, 80. So at 50, 80, the value of the gradient is going to be -0.02 times 50, that's -1. And then -0.04 times 80, that's -3.2. So now I can find the value of the directional derivative of f at 50, 80. It's going to be -1, -3.2, dot that with my unit vector u, 0, -1, and I'm going to get positive 3.2. Now remember, that represents the rate of change of z, so that would be meters of elevation per change in the xy plane. So you could just say meter of distance, right, that you moved in the xy plane. All right, so are you ascending or descending? Did you figure it out? Well, since the value of the directional derivative is positive, that means you're going uphill, z is increasing, so we are ascending. All right, part B. If you walk northwest, will you start to ascend or descend, and then at what rate? So northwest, we need a unit vector that takes us in that direction. Not bad, unless you just get jumbled up which way west is. It's over here, people, where the negative x-axis is. Okay, so if you're walking northwest from 50, 80, what unit vector could you use to say this direction right here? Well, the components would be -1, 1, but then make sure it's a unit vector, so I would divide by rad 2. So you would have components 1 over rad 2 times -1, 1. And then I already have my gradient at p, so this directional derivative is going to be easy. We did all that extra work up above. So I'm going to take the dot product with the same gradient, -1, -3.2, with this new direction u, 1 over rad 2 times -1, 1. So this is going to give me +1 minus 3.2 divided by the square root of 2, which is -2.2 divided by rad 2. And remember, that's meters of elevation per meter of distance. So what would you say about this rate of change? Are you ascending or descending? Well, notice it's negative, which means we are descending. You're going downhill. All right, next part. In which direction is the slope the largest? So when is the rate of change a max? Oh, in the direction of the gradient. So in the direction of the gradient of f, which has components -1, -3.2. Second part of the question, what is that rate of ascent? Well, we have that theorem that tells us that that actual max rate can be found by taking the magnitude of the gradient. So the magnitude is going to be the square root of 1 squared plus 3.2 squared, which is about 3.35 meters, remember, of elevation per meter of distance. Okay, at what angle above the horizontal does the path in that direction begin? Okay, so what I want to know is, what is the angle theta where, oh, that's a terrible triangle, hold on, where this rate of ascent, this is z, is equal to 3.35, right? That's giving me the change in z. So that's 3.35 meters, and then that's per 1 meter of distance. You could think of this as 3.35 change in z over 1 meter change in the xy plane. So this side's 1, this side here is 3.35. I don't like how I labeled that 1. This side down here is 1, and then they want that angle theta that's right in there. Okay, so tangent of theta is equal to 3.35 over 1. So theta is approximately 73.4 degrees. All right, what a nice little example. Now we're going to look at how the gradient can be used to simplify finding tangent planes to surfaces. Remember, we talked about that a few lessons ago. And so now we want to revisit the topic now that we know something about the gradient. Okay, now assume S is a surface and it satisfies that it's a function of x, y, and z equal to some constant k. And say we have a point P with coordinates x naught, y naught, z naught, and that's a point on the surface S. And now C is any curve which I can represent parametrically. So I'll call it R of t with components x, y, and z, all functions of t. And this curve C lies on the surface. Okay? Now say I want to differentiate f with respect to t. Okay, so I have my function of x, y, z equal to k, and now I want to differentiate it with respect to t. Well, remember, since f is a function of x, y, and z, I'm going to have to apply the chain rule, so I'll have del f del x times, now x is just a function of t, so that would be dx dt, not a partial, plus del f del y times dy dt, plus del f del z times dz dt is equal to 0, because k is a constant. Okay, well, look at this derivative here. Doesn't it remind you of the dot product just a little bit? It sure reminds me of a dot product. Look, let's see if we can come up with the two vectors that were dotted. It looks like one of them was del f del x, del f del y, del f del z. And what's the other one? dx dt, dy dt, and dz dt. And this equals 0. That's interesting. Who's this? This is our good friend, the gradient. That's the gradient of f dotted with, well, remember, R, my curve, had components x, y, and z. So this vector here is just r prime of t. And interestingly, the gradient of f dotted with r prime of t gives me 0. What does that mean? They're orthogonal. So this tells me that the gradient of f is orthogonal to the tangent, right? R prime would be tangent to any curve on S that goes through P. So basically the gradient of f acts as the normal vector to our tangent. exciting. Okay, so that means the tangent plane to the level surface f of xyz equaling k at some point P is given by using n equal to the gradient of f evaluated at x naught, y naught, z naught as the normal vector. And then from there, you're going to make sure you write your final equation in standard linear form. Ax plus by plus cz equaling d. Okay? All right, so now we can find equations of tangent planes to surfaces, not necessarily only when z is defined as a function of x and y. So here, let's look at an example. Find the tangent plane to the following surface at -1, 1, 2. So I'm after that normal vector, which is going to be the gradient. And since this is equal to a constant, I'm just going to go ahead, take my partial derivative. So partial with respect to x is going to be 2x. Partial with respect to y is going to be -4y. And then partial with respect to z is 2z. And then now I need to evaluate that at the point P, -1, 1, -2. So first component is going to be -2, -4, and -4. Well, I could use that, or I could also use for n +1, 2, 2, which is just a little nicer to work with. So let's go ahead and do that. So I'll have 1 times x plus 1. Remember, I'm using this point here as the point on the plane, plus 2 times y minus 1, plus 2 times z plus 2 is equal to 0. And then we get x plus 2y plus 2z is equal to -3. All right, pretty straightforward. Now, another term here is the normal line. We say the normal line to a surface at some point P is the line that goes through P and it's perpendicular to the tangent plane. So therefore, if this normal line is perpendicular to the tangent plane, its direction vector is going to be in the same direction as that normal vector, the gradient vector. So the normal line could be found by taking the gradient of f at P as the direction vector. And then use P as the point to write the parametric equations for this normal line. So let's look at an example, pretty straightforward. Same surface as before. Now I want to write the equation of the normal line. Well, remember, we have the gradient of f at that point from earlier, and we found it to be -2, -4, -4. You could use that, or it's a lot nicer just to work with 1, 2, 2. And then I can go ahead and write the parametric equations for the normal line. So x is going to equal, remember I take that first component and I'll have multiply that by t. So I'll have t minus 1. Y is going to equal 2t plus 1. Remember I'm using the point there. And z is equal to 2t minus 2. So here are the parametric equations for that normal line. All right, just to tie this all into when we talked about tangent planes before, we said that if z was a function of x and y, then the tangent plane was found by looking at the normal vector with components partial with respect to x, partial with respect to y, and -1. But now we see that this was just a special case of our new approach. Because if z is a function of x and y, I could redefine this as a function of x and y and z. I'll call it capital F of x, y, z. And remember, it needs to equal a constant. So I could write f of x, y minus z is equal to 0. And now if I take the gradient of f, I would have the partial with respect to x, partial with respect to y, and -1, which is my normal vector. So we were just dealing with a special case before. So look at this gradient. It has so many uses. Let's just summarize what we've considered so far. The gradient is useful for, well, it gives us the normal vector, right, for a tangent plane. What else? It gives us the direction vector. For the normal line. It also gives us the direction for the greatest rate of increase. And the opposite of the gradient gives the direction for the greatest rate of decrease. Oh, there's more. The magnitude of the gradient gives that fastest rate of increase, not fattest, fastest. And the opposite of the magnitude of the gradient gives us the fastest rate of decrease. Change this to decrease. Okay. Also, there's more. The gradient is orthogonal to level curves. Remember, we showed that the gradient dotted with r prime of t was equal to 0. And the gradient is used to find directional derivatives. The summary is basically in reverse. This was the first thing we considered. Remember directional derivatives from the very beginning of the video? Okay, so last example, way to go. So find the points on the surface where the tangent plane is parallel to this plane here. Okay, well, what's the normal vector for this plane? The normal vector has components 3, -1, 3. All right. So I want to know where's the gradient of this surface, the gradient of f equal to k times n, where k is a scalar. Okay, well, the gradient of f, we can find that easily. That's 2x, 4y, 6z. How about instead we divide that whole thing by 2 and just use x, 2y, 3z, right? Why not? So I want to know, when is that equal to k times the normal vector for this other plane? Because then those two planes would be parallel. All right, well, let's see. We have a little system going on here. I could set x equal to 3k. Let's do that. So x is equal to 3k. 2y would equal -k. And also 3z would equal 3k. And now I want to make sure this point is on the surface. So I'm going to say, well, I'll keep x is equal to 3k. Y is equal to -k/2. And z is equal to k. So I'm going to substitute these in for x, y, and z into the surface. I'll find k first, and then I'll find the points where the tangent plane is parallel to the other plane. Okay, so we're plugging all of this in to x squared plus 2y squared plus 3z squared is 1. So I'm going to have x was 3k, right? So 3k squared plus 2 times -k/2 squared plus 3 times z is just k squared is 1. So what is that? 9k squared plus 1/2 k squared plus another 9k squared. So this is going to give me 25 over, no, excuse me, I have 9k squared. That one's going to be a half and then just a 3, right? So 25 over 2k squared equals 1, which means that k squared equals 2 over 25. So k equals plus or minus rad 2 over 5. All right, well, we have a couple possibilities then. So let's list everything out nicely. To begin, if k is equal to positive rad 2 over 5, then x would be 3 times that, so 3 rad 2 over 5. Y is negative rad 2 over 10, and then z would be equal to k, so rad 2 over 5. Now, if k is equal to negative rad 2 over 5, then x would be negative 3 rad 2 over 5. Y would be positive rad 2 over 10, and z would be negative rad 2 over 5. So that's one option of how to write it out. You can't just put plus or minus across, but I'll show you another way that you could write it if you don't want to write out the 2 points separately. Here's your other option. It's pretty slick. Or you could write out your answer as plus or minus 3 rad 2 over 5. Now notice, whatever sign the x coordinate had, the y coordinate had the opposite sign, right? See how these are opposites? So to indicate that they're always opposite, then for the next coordinate, I would put minus plus rad 2 over 10. And then the z coordinate matches the sign of the x coordinate, so that would be plus or minus rad 2 over 5. Okay, but you can't put plus or minus for all of them. I love this. The less I write, the happier I am. You know what I mean? Looks good. So that concludes the lesson. It was a beast of one, but so interesting and so useful.